Okay, and the last question, number 9. A dentist uses a small mirror of radius 40 millimeters. So if the radius is 40 millimeters, then it means the focal length is 20 millimeters. To locate a cavity in a patient's tooth, the mirror is concave and held 16 millimeters from the tooth. So the DO is 16 millimeters. And it wants to know what is the magnification. So first step, find the DI. So 1 over F equals 1 over DO plus 1 over DI. So 1 over DI equals 1 over F minus 1 over DO. So 1 over DI is equal to 1 over 20 minus 1 over 16. 320. There might be an easier one. 80? Yeah, 80. So 4 over 80 minus 5 over 80. So DI is equal to 1 over DI is equal to negative 1 over 80. So DI is equal to negative 80. Where the negative, of course, means virtual. But it wants magnification, so we know magnification is negative DI over DO. So negative 80 becomes positive 80, and DO is 16. So the magnification is 5. And sometimes on magnification we put it times. Okay, so I have a few more mirror ones for you for tonight, but and one other mirror thing to talk to you about that I should have, it was cool that I mentioned yesterday, and I missed the cool part. Spherical aberration we talked about yesterday. And in spherical aberration, it's where... Okay, I'll use that, never mind. It's where light rays coming in parallel to the principal axis cross before the mirror before the F instead of right at F. And the result is a blurry image. And we said that you could fix it by using a parabolic mirror. So the cool piece that I forgot to mention was the Hubble Telescope. The Hubble Telescope, the people that made the mirror in it, made a mistake, made an error when they were grinding the mirror. And so they were off by 0.2 micrometers. So 0.000, or 2, not 0.2, 002 meters. And as a result, instead of it focusing 70% of the light at the focal point, it can only focus 15%. Imagine. And it would cost millions to fix that, which they probably did fix before they sent it up there, but I suspect a few people lost their jobs. So instead of it focusing 70%, by being off by 2 micrometers, look at the percentage of light that dropped. Okay, so that was spherical, the end of spherical aberration that I wanted to mention to you. All right, we are going to start images formed by refraction. So in mirrors, it's always reflection that's going on. But now it's images formed by refraction. Refraction is when light passes from one medium to another, and as it passes, the media have different densities, so the light gets bent. So light passing through something must be lenses. And there are 2 different types of lenses. One that looks like this, and one that looks like this. This one is called a convex lens. And singular is, there's no E. And this one is a concave lens. Okay? They're going to be very similar to our mirrors, right? Convex and concave. The convex one bulges out. The concave one caves in. Okay? And maybe a lens is simply a disc of transparent material. It could be made of plastic, it could be made of glass, but it has curved surfaces. And when light passes through these discs, because of the curved surfaces, it's going to get bent. Okay? Now, here's the thing. Remember, concave mirrors were converging and convex mirrors were diverging? Well, now convex lenses are the converging ones. And the concave ones are the diverging. So hopefully you got the mirrors straight, because otherwise I'm going to mess you up. Really, I often think of this is like it's two convex mirrors put back to back, and this is like two concave mirrors put back to back. We are going to look at converging ones first, just like we did in mirrors. So converging lenses, which are convex lenses. Okay? A few things to identify. So draw the line straight through. I said think of this as two mirrors back to back. So if this was a convex mirror and this was a convex mirror, each one of them would have an F on either side. Okay? And so lenses have an F on both sides. It's why you could take a lens like a magnifying glass and you can put it either here or here. Like you can turn it either way and it still works. Okay? So there's an F on either side. And instead of C this time, we use the point 2F. Okay, because I guess it's not really going to be a sphere now. And so instead of a center of curvature, we have F and 2F. And the other point that's important in a lens is this point, the O. It's the optical center. I guess I didn't say about the 2F, but I think you could probably guess it's twice as far from the lens as the F is. And the line going straight through is still called the principal axis. Okay? Now, this is a converging lens, and it's because we're going to have three rays that we can use to locate objects. And one of them is a ray that goes in parallel to the principal axis. This time it's going to refract through the lens, so it's actually going to pass through. And I'm drawing these little lines. These are the normals, because remember when you go from less to more, LM, it bends towards the normal. And now we're going from more dense to less dense. It's going to bend away from the normal. And it's going to pass through F. So if I do the same one going in parallel to the principal axis, it's going to get bent in such a way that it passes through F on this side. And this is why a convex lens is converging. Light rays converge. Okay? So there are three rays that we can use to locate images in a convex lens. So label your F, label your 2F on this side, your F, your 2F. Okay? And ray 1 is what we just did. A ray going in parallel to the principal axis is going to get bent in such a way that it passes through F. Whoops, imagine that I passed through F there. Through F on the opposite side of the lens. That is ray 1. A ray going in parallel to the principal axis gets bent in such a way that it passes through F on the opposite side of the lens. Second ray is a ray that goes in through F. I'm going to turn my paper to do this one. Lost my pen cap. Sorry. A ray that goes in through F. I'll turn it back as soon as I draw this diagonal line. A ray that goes in through F, strikes the lens, and gets bent in such a way that it comes out parallel to the principal axis. This is ray 2. This should sound familiar. They are actually identical to the two of the rays that we were using to find images in the converging mirrors. The third one in the converging mirrors, the concave mirrors, was a ray going in through C. But this time, it's going to be a ray passing through the O. So a ray passing through the optical center of the lens passes straight through without getting refracted. Okay, so that means it's hitting the normal on either side here, and it's going to pass